I'm going to start us with a video. I hope it comes through okay.
Oh, that was awesome.
Oh, so that was Mars sample return. That's what I work on at JPL. This talk, I'll talk about kind of what it takes to get that done, what it takes to get samples back from Mars. We've never had any samples back from Mars before. We've sent a lot of stuff to Mars, never gotten anything back, and we stand to learn a lot from being able to bring those back. This is a cool image that I love. This is a map of the Jezero crater region of Mars, which is where currently the Perseverance rover, which landed on Mars 3 years ago or so, has been operating and collecting samples, putting them in tubes, and we're going to go and get them quite soon. So what does it take? That's what I'm going to talk about today. To start off with, though, a bit about me. I was born in India, but I moved to the States pretty young in the year 2000. I've spent most of my time in the Midwest, growing up in the Midwest, and went to school in UMich for both undergrad and grad school, as Elliot mentioned. But currently, I live and work in Los Angeles. That's where Jet Propulsion Lab is. And I love living here, mostly to do stuff outdoors. So big fan of rock climbing. This is me doing some sport climbing in Malibu Creek, which is kind of a local state park. And then this is me on Mount Whitney at about 13,000 feet at like 3 a.m. in the snow and ice, working on an ascent a few months ago. So, but before we get to talking about JPL and Mars and how to get samples back, I'm going to talk about how we went about doing things at UMich, some key experiences and some takeaways. Then we'll get to JPL and I'll give you some advice, some pretty cheesy advice, but hopefully it'll be helpful for you all. All right, great. So this is what UMich looked like for me, grossly speaking. So I came in at around 2015, well, fall of 2015, and declared mechanical engineering. That had always been an interest of mine. I took the intro programming class, Engineering 101, it was required, and I really liked it. So I declared a CS minor, and I kept really liking it. So I made that a double major. It turns out when you double major in engineering, they give you 2 degrees, which is cool. And then I got more and more into robotics, more into the electronics and embedded system side of it as well. So then I changed that CS to a CE, and so I wrapped up undergrad in 2020, basically right after COVID hit, and but jumped into the master's in robotics from there. During undergrad, one of the big things I worked on was mRover project team. You may have heard of. I'll talk about that coming up in a second. I was interning at JPL. I did that twice. I also spent a long time teaching ME350, which is a junior level lab course. I'll explain that as we get along as well. And then in grad school, I really turned my focus to research, particularly in Ember Lab under Talia Moore, as well as collaborating with Elliot. So that's fun. So let me start with some of the undergrad stuff, particularly MRover. So if you're not familiar, MRover is a student-run robotics team competing in the University Rover Challenge, URC. The challenge is basically, it's a prompt for 36 teams from around the world to field a robot about 50 kilograms. So think like a lawn car, like that kids have to ride around in the on their lawns. Involves things like rough terrain traversal, manipulation with a robotic arm or something like that, sampling and analysis. And I forgot to put an important bullet point on here, which is like autonomous navigation. So a pretty diverse set of challenges. It's really fun, really ambitious. And I got involved as a sophomore and started working on hardware stuff pretty much right away. So started off really focused on mechanism design. So here on the right, this is a rotary percussive drill that we built for the sampling portion of the competition. So we had to sample dirt at the competition site, which is in Utah, and analyze it on board, analyze it off board as well, and produce some scientific conclusions. Worked a lot on hardware fabrication. So these are all parts that I made in the Wilson Center on the machines. Learned a lot about how materials work, how to build things, gained a much better intuition for hardware design. Also had a lot of fun, a lot of late nights. And then started kind of branching out from the pure mechanical stuff. So I got into a bit of instrumentation design. This is an optical spectrometer that we built also for that sample analysis task of competition. Really new frontier for me, learning about optics and stuff. I had the intro physics courses or whatever, but really, again, threw myself in the deep end. But it's a blast. Moving forward, got more into the robotics aspect. So this is a project I did actually for my computer engineering capstone, which was to build this robotic arm with the team, of course, but then write the forward and inverse kinematics, the motion planning, and the control, as well as a user interface. Actually, I don't have an image of that for using this arm kind of way more effectively than we had been. We had this janky teleoperation scheme. This ended up also being janky, but nonetheless, a really intense foray into robotics. This was under Chad Jenkins actually in EECS 467. That was a lot of fun. And also got into electronics. So this is a prototype of a brushless motor controller. And this was an exercise in both like power electronics design and firmware and embedded systems. So overall, these were like really ambitious projects over a really diverse set of skills. Bunch of failures. These were big steps up compared to what we had been doing on the team like before those. All of these things kind of between these two slides, they like hardly worked. But nonetheless, it was worth doing, and it was a great source of learning for me and my teammates. However, on top of the technical stuff, I probably spent more time building the team than building hardware and building rovers for the team. So when I joined in 2016, which is competition year 2017. It was a really small team, super scrappy, about 20 people, honestly, probably less than 20 people. I don't remember exactly. Pretty small budget. There were hardly any people on the team. So I was asked to like just start as a sub-team lead, throw in the deep end. But really enjoyed it, really liked working with the people on the team. So the next year I came back as chief engineer and spent a lot of effort growing the team along with a few other of my peers in the leadership. So we doubled the size of the team, doubled the budget, took on a bunch of ambitious technical projects, and improved our standing drastically. So we jumped over to 9th, first time in the top 10. Okay, kept doing that. So as chief engineer, I was working on technical stuff, but also in that team growth part of it, a lot of coaching, training, recruiting people, helping them get what they wanted out of the team so that they'd stay. And I kept doing that as a senior advising mentor, focused on even more. Once again, double the size of the team. Once again, improved the standing to about 7th. And then fast forward a few years, mRover made their first place finish out of 36, and the growth has continued. So at this point, I'm just an alumni, but nonetheless, it's really fun to watch this trajectory. Achieving this growth was way more work than any of the technical stuff. It involved a lot of really a lot of reflection on how the team was running, a lot of intentional discussions with people in the leadership, with people not in the leadership, about how do we make sure that people are growing and getting what they want out of this. We want to keep these people around. We want them to train the next generation, etc. So growing the team like this was a whole nother set of skills outside of just the engineering that was super rewarding. And just like the technical stuff, I said it was ambitious and it didn't always work. Same thing with this kind of leadership and teamwork. We did a lot of experiments on how to run the team and how to organize the team, etc. And not all of them work. So failing in that regard and recovering was also kind of a key experience. So mRover, great time. I'm sure at least some of you in the room are part of mRover. I hope so anyway. But let me jump over to some grad school stuff. Oh wait, no, I have some fun photos first that I was talking about with Kyle before we started actually. This is kind of a small photo, but this is me and my East for 67 team with Chad at the final convention or final like design expo thing, showing off the arm. Here's the second rover I worked on. It's called Phoebe, in front of the future site of the robotics building. So this right here is where the robotics building is right now. So kind of cool. When I came to school, this was just a parking lot. As it is in this photo, it's a dirt lot. Fast forward a few months, this is me and some of my teammates and our advisor, Lynn Van Neustadt, with the rover at the groundbreaking ceremony. So they set up a tent in that dirt lot and brought in, all the big wigs. Like I think the governor was there and like politicians and corporate sponsors, etc. They got to check out our rover. I think the tent was probably around where the stairwell is right now, something like that, in the atrium. Keep going. Here's the main structure, of the building up where we keep testing our rover on this lot, on this grass outside the naval building. It was fun watching the building go up while we were doing that. And then even more forward, now the building's got glass on it. These were some first looks at the Mars yard, which mRover had a part in designing. So that's fun. This is another event we did with robotics. It was a UMich tailgate. It's like the Alumni Association tailgate or something. The robotics department brought us through. And this is NASA Administrator Jim Bridenstine at the time. He has this custom Wolverines logo jersey that says NASA on the back, which is pretty cool. So you got to check out our rover as well. Really fun times, really key experience during my undergrad. So I'm going to jump over to grad school stuff. As I mentioned before, I worked in Ember Lab under Talia Moore. The lab studies the interplay between robots and biology. And there's kind of two sides of the coin. Robots for biology is one. How can we use robots as tools to improve how we study animals? So that can be tools to interact with animals, to stand in for animals. There are things that you can test on robots that you can't test on animals. So we'll talk about this in a second, but like you can't just take an animal's leg and flip it around. You can do that on a robot and see what it does to the motion. Okay, and then the other side is biology for robots. By looking at how animals move and act, think, and react to things, can we make robots better? We have several animal-like robots in the building, legged robots, mostly in the walk lab downstairs, that are animal-like, but they are nowhere near the capability of almost any animal in nature. All right, so there's a lot to learn from biology in improving robots. Okay, so I worked on legged robots. The this is a smattering of some popular legged robots in the field right now. We have a Spot and an Animal in the building, I think in the walk lab. These are really cool. They're really capable. However, they don't really look like animals. You'll notice like all of them have identical legs. Animals don't have identical legs. They're super symmetrical. And there are a number of other properties that really set them apart from animals that limit their applicability to some of the stuff that we'd like to do in the lab. Right. So these aren't really built for use by biologists, and they're crazy expensive. That's another thing. Can we address this? Can we make legged robots that are more useful for studying biology and studying motion in a fundamental sense? Well, we set out to do that and started with actuators. Actuators are basically like motors plus the control and other hardware that's necessary to make them act usefully on a robot. They're often the most expensive parts of robots. Okay, so can we make them cheaper, but still retain, the key capability? And the answer is actually yes, and we did that with these. Okay, so I worked on the mechanical and thermal design for 2 variants of this actuator. Figured out how to build them out of just 3D printers and hand tools, so no like custom machine components or anything. In the grand scale, relatively easy to build. And not even in the grand scale, I like to think they're relatively easy to build. And then once building them, did some really rigorous system identification and characterization to prove that these actuators are ready for use or appropriate for use on high performance robots, and they were. So we presented this work at IROS last year in Japan. It was a blast. The paper, you can find the paper on umbrolab.com. I probably should have put in a QR code or something. But this is really fun. You can also check out the actuators in the lab, I think. Okay, so next step from that, building a whole robot. So we took those actuators, built a bunch of them, and built this quadrupedal robot called Trot, which is also 3D printed, which is also really easy to build. You don't need like really specialized tools and stuff, and really easy to reconfigure. So we're working on our first few publications with this robot. Jessie Carlson is really leading this right now. So if you want to know more about it, maybe talk to her. Sorry for volunteering you, Jessie, if you're around there. But maybe you all have seen this around the building too. I don't know how much it makes it out of the lab, but this was a really rewarding experience. Really refined things that I learned in undergrad, and both technical skills and like organization skills. I built up a team. Like it wasn't just me. Recruited people, and it was really different in that this is an open-ended problem. So on umrover, there's a competition task. In research, you kind of need to set your own goals, figure out what's a good goal to set and what's a good contribution to make, and then make it and adapt to it. So great time. And then the last bit I'll talk about in my time at UMich here is 7 semesters teaching ME 350. So this spanned between both undergrad and grad school. The course is kind of like a robotics course in many senses. So let me play this video. Students have to build this linkage mechanism. So it's like a single degree of freedom robot that catches these balls coming out of these tubes, detects the color of it, and then based on the color, either throws it into the net, which is kind of this black rim back there, or into this transparent box. So you'll see, this is a slow-mo video, by the way. So it's got to do that as fast as possible. There's a competitive aspect to it. And students have to, design the linkage for the right kinematics, design the actuation system, design the control system on a microcontroller, tune it, refine it, etc. So really fun project. The project's changed since then. It changes every few semesters, but it always contains those elements. Teaching this course was probably the most important thing I did at UMich. Like of the map I showed on like slide 3 or whatever, if you had to choose one between like doing another major or a project team or research or something, or teaching, I would choose teaching. So one, you've probably heard that if you can teach something to someone, that means you have like true mastery over that topic. I completely agree. I had to refine my knowledge a lot of mechatronics and mechanical engineering to teach this course. And people like to joke that I have a degree in this course because this is almost like 4 years worth of teaching. But also there's a whole different set of skills outside of the engineering. That was more in line with some of the stuff I was talking about with growing mRover, which is like getting to know my students on a really individual basis, understanding their background, understanding what they wanted to get out of the course, what their strengths and weaknesses were, and then taking them through milestone by milestone to the finish line. Incredibly rewarding. Taught me a bunch of skills that I don't think I would have learned as effectively in other ways. So if you have the opportunity to teach, whether it's formally like as an IA or a GSI or as part of a team or I don't know, to your friends, like take that opportunity. It's really quite important. Okay, so like on that note, I just want to talk about the videos always mess me up on slide progression. There we go. Some of my takeaways from my time at UMich here. So find people who push you, who do it nicely anyway. The only reason that I kind of was so ambitious while I was in school was because I had people around me who really recognized potential in me and pushed me to try these things. It was really important because it wasn't like I succeeded at everything, but having the ambition and the will to try something knowing you might fail is really important. And now I feel much more confident when I'm trying new things, which is important. You'll see at JPL we're trying new things, pretty new things. That also means push your peers, but do it nicely. Those same people who pushed me are also people who cared about me. So find people who care about you, which also means care for your peers and take care of yourself. I think a lot of people, at least a lot of my friends, had this thought after leaving college, like, oh, I should have taken better care of myself. I definitely didn't. So take care of yourself, mentally, physically, across the board. It's important. Okay, and then of course, build things. I think the robotics department has a pretty good focus on this. I think people are pretty enthusiastic about building things, building robots, but also take some time to build teams. Try to start up a team. It may not work out, but give it a try, or try to lead a team that already exists. Okay, and then this is really important. Even though I didn't really talk about it much in the previous slides, learn about more than one subject, particularly outside of engineering. I didn't speak about this through slides, but while I was doing robotics and engineering stuff, I was also working with MFA students, like art students working on their final theses, like helping them build their installations, like really big art installations. It was fun. I was working with visiting artists, helping them with like gallery installations here. It's really important to meet people who think in other ways, engage with different material, and to connect it back to robotics, I like to say that this is basically like domain randomization and reinforcement learning. If you're not familiar with reinforcement learning, it's basically a technique where you give a robot some way of evaluating itself if it's doing a good job or a bad job, or a simulation of a robot, and have it try a bunch of random things and focus on the things that evaluate as doing a good job. One way to get even better results out of this process is through something called domain randomization, where you make the robot or the simulation do things in random environments where you randomize different parameters, change fundamentally what it's doing, and you end up with a much more robust and much more like generalized solution. Right now, you all are in school learning how to learn. You're learning robotics, but you're learning how to learn. You're not going to learn everything about robotics during school. You'll have to keep learning as you go on outside of school. If you can put yourself in randomized environments, let's say, or like different environments, learning different things, you will be much better at learning. It happens really quickly, shockingly quickly, actually. So I'd really recommend doing that, especially whether it's just taking courses outside of engineering. I wish there was more time and opportunity to take courses outside of engineering in the way the programs are set up. But see if you can make that a priority, or outside of classes, things like that. So Kind of the key thing though to wrap this all up is that the outcome of school is you as a whole person, not just a transcript or resume or a portfolio. Any of these opportunities to do cool things, the outcome is not like, for example, on MRover, like this competition doesn't exist such that the outcome is like some team getting podium or like your team getting podium. The outcome is for there to be a group of people who like working together, who like working on engineering, who know how to work on a team and work towards a goal. So the outcome is those people, and those people are you, right? So it's not the podium finish or whatever. Okay, let's talk about JPL. Quick overview. Elliot explained a little bit, but NASA Jet Propulsion Lab, JPL, it's one of 10 major NASA centers. Technically, it predates NASA. It's called Jet Propulsion Lab, but Jet Propulsion is no longer the focus. Really, space robotics is the focus. It's also part of Caltech. About 6,000 people, so fairly big actually, and responsible for all successful Mars rover missions and a whole bunch of other stuff from other planets, other objects in the solar system, around Earth, Earth's surface, like huge portfolio of stuff. Interned there twice during undergrad, and now I'm there full time for the last almost year and a half as a mechatronics engineer. I work on Mars spacecraft actuators. So let me explain more about that in a few slides. But first, I want to explain some things that you saw in that video up front. What was going on there, right? So that was Mars sample return. The first thing you saw was the Perseverance rover. This rover is already on Mars. It's already doing things. But it's more than just a rover. It's really 5 robots in one. So first it had to leave Earth on a launch vehicle, a rocket. This is not just a stick that produces thrust. It's a full robot. It has to act intelligently, respond to input, respond to disturbances, actuate, reason, act, perceive, etc. It's a full-on robot. Okay, same with the cruise stage. This is what the rover looks like all packaged up in an aeroshell and a heat shield as it traverses interplanetary space. This is doing all those same things. This is also a robot. Okay, and then when we get to Mars, we have to land. The rovers land via this thing called a sky crane, which is a rocket-powered jetpack. It comes in from like mid to low atmosphere and orients the rover and stabilizes and then descends to a hover position above the surface and slowly lowers the rover down. It's a pretty complex control problem, and it's doing all those same things. It's thinking, it's responding to input, perceiving, acting, reasoning, etc. And then, of course, we have the robot, and the robot was also carrying this helicopter, the Ingenuity helicopter. This is the first rotorcraft to be flown on another planet ever. So really cool. This mission, 5 robots in one. Pretty neat. When I was an intern, I worked on this tower on the front. This is called the remote sensing mast. It's got a gimbal head with a bunch of cameras and other instruments on it. Here's me in the clean room building it. This is a gold-plated camera. I can explain more about that in the Q&A, why it's gold-plated, but it is. Pretty cool. Okay, other thing you saw was sample return lander. It's a lander, not a rover, because it lands and it just stays there. It doesn't have wheels. Absolutely massive. It's like 3 tons, like 3,000 kilograms. Think about like 15 feet in diameter or something. Huge, huge, huge spacecraft. Similar thing, a bunch of robots in one. This hasn't launched yet. This is in the next few years. Launch vehicle is a robot. Cruise stage is a robot. This doesn't have a sky crane. It's kind of its own sky crane, but still it's operating as a different robot than when it lands. Once it lands, it's a stationary robot. The lander itself has a robotic arm and a bunch of other mechanisms in order to take those samples in that we saw in the video. That rover brought up the sample tubes, put them in the lander. It's also likely going to have 2 helicopters. This wasn't in the video because the video was made like last year, I think. These 2 helicopters are going to be iterations on the Ingenuity helicopter. And then finally, probably the coolest part, arguably anyway, is the MAV, the Mars Ascent vehicle. The reason the spacecraft is so big is because it has a rocket inside of it that's going to take those samples that were deposited into the lander and put them into Mars orbit. Okay, and this, just like the launch vehicle, this MAV is its own robot. Okay, so sample return lander, it's really 7 robots in one. Now I can finally tell you a little bit of what I work on. I work on actuators on SRL. This door in the front, this is where the samples get inserted. It opens and closes, so my actuator opens and closes that door. There are 4 landing legs that expand and contract to stabilize the lander. So my actuator powers those. And then on top, not visible in the video, are the 2 heli deploy actuators that move the helis from a stowed position into a position where they can take off. So I do those actuators. There's 7 total actuators that I work on this spacecraft. I do actuator design, actuator and mechanism dynamics, which really drives the design, precision fabrication stuff, characterization. Once the actuators are built anyway, I'll be doing characterization. And I have just so many interfaces. The mechanism teams, the people who work on that landing leg and that door and the helicopters, the mechanism teams, the motor control team, the software team, structural team, several external companies. There are a lot of external companies involved. I'll explain that more in a few slides. But yeah, really big job, really related to what I was doing at UMich in grad school. So it's been a good fit. It's been really fun. Okay, we can talk more about actuators later. Because you also saw something else. This is the Earth Return Orbiter, ERO. This doesn't land on Mars, but it orbits Mars. And it catches that sample that the MAV puts into orbit. It catches it in space and then packages it up into the Earth entry system. So similarly, it's a collection of robots. Launch vehicle, the orbiter itself, which also kind of crosses the interplanetary space. It's got robots inside to manipulate those samples. And then it deploys this entirely separate spacecraft that has the samples in it to return to Earth. So 4 robots in one. You know, we had 5 on the rover, 7 on the lander, 4 here, 16 robots total. And one could argue there's more depending on how you want to split things up. I'm trying to go pretty coarse here, honestly. Super complex, super ambitious, but really exciting, right? So in case you haven't perceived this as challenging yet, let me explain what the challenge is. You know, because earlier I was talking about stuff at UMich, right? On mRover, we'd build a robot in a year with less than 100 people, a few $10,000. In grad school, we built this legged robot in about 2 years, less than 10 people, really small team. Same, like pretty low cost price point. Doing this, Mars sample return, these 3 big projects, 16 robots, we're talking thousands of people, billions of dollars in 20 years. You could actually argue it's longer than 20 years, depending on how you want to slice it. But the rover development started 10 years ago, and we won't have the samples back on Earth for another 10 years minimum. Okay, so this is like several orders of magnitude different in scope. You know, why is that the case? Of course, there's the robotics aspect. Honestly, I'm not even going to talk about this too much because you all are going to be the experts on this soon. But many robotics challenges involved on these spacecraft. But there's all sorts of stuff on top of that. Okay, one, robustness. These things just like can't fail. Huge public investment, tons of time spent, thousands of people involved. Like there's no appetite for any of this to fail. We build in as many redundancies as we can, but ultimately there are these interdependencies where things become bottlenecks, things become single point failures, and our only choice is to just engineer extremely well and test a lot, of course. Okay, on top of that, we have to be robust in a bunch of environments. We're not just building robots for Mars. We're building robots for rigorous testing on Earth. Testing done by interns like me, you know, that's dangerous. That's a dangerous environment for a robot. Robots that need to survive rocket launch, interplanetary space. So this is like, in space, it's like negative 200 degrees Celsius. Things got heaters and stuff. And it takes like a year. So you're taking a robot and putting in a freezer, a really deep freezer for a year, and then taking it out and it needs to work flawlessly the first time it comes out. Okay, it needs to survive Martian atmospheric entry and landing. You're going from space to land in a few minutes. It's quite violent, quite intense. And then finally, we actually get to the Martian surface operations, right? So that is all to say, like if we had the ability to just teleport a robot to the Martian surface to do the mission, that robot would look much, much different than what we actually have to build, because what we actually have to build has to go through this whole pipeline. Okay, that really amplifies the challenge. On top of that, we have really, really tight constraints. Mass, volume, energy, computation. This is something that might not be obvious. The computers we have on Earth are extremely powerful for their size. However, they are not space grade. They're super sensitive to radiation. Things are protected from radiation here on Earth, but in space, they're not. The computers that are space grade are not nearly as powerful. Okay, so that really limits us in terms of what kind of algorithms and robotic techniques we can deploy, and have to get really clever about it. Okay, and really the greatest challenge though is executing. Under all of these constraints, all of these requirements, executing on a timeline, under a budget with like a non-infinite workforce. And that's really the challenge. So what does it take? It takes a whole bunch of people. So this is kind of the MSR, part of the MSR team. I don't even know all of the companies and stuff involved. I don't have all the logos, but at the top level, it's a collaboration between NASA and European Space Agency, ESA. But we have several NASA centers involved, many American companies, many European companies, and many more, like I said, that I don't even know about or don't have room to put on the slide here. So 16 robots, many organizations, thousands of people of all disciplines, engineering, non-engineering, business, art, PR, like it's all relevant. Okay, so that's the challenge. Let me dig into it a bit. What it really takes to execute are all of those people and their relationships. This is a photo of the Perseverance rover team, just a subset of the Perseverance rover team and a subset of the folks on that team that are at JPL. And there's probably like 800, maybe 500 people in this photo. I don't know. Okay, all of these people that are in the photo and not in the photo are like nodes in a web. So at some point in your education, you'll learn about graph theory. But the important thing about a web or a graph, like the thing that gives it significance, are the edges, like how the nodes are connected. For a team, these are the interpersonal connections that really make the web do anything. All right, this is an extremely complex mission. The only pathway to success basically requires focused engagement of thousands of people over like 3 to 10 years. That's really, really hard to get. So in college, you might work on a team of somewhere between 5 to 100 people for like a year or a semester, or maybe several years, depending on what you're doing. So this is an extreme challenge that's hard to express until you really witness it. Right? Like, how do you get focused engagement from thousands of people over many years? Really, the key is these aspects here. Respect for each other at every level between everyone. Social acceptance, social cohesion, good culture, basically. A reasonable workload, and coaching and training and career growth. People love to grow. That's just what people do. That's what people look for. All of this is central and key to mission success. It's more important than pretty much any single technical innovation or any several technical innovations. And I'm just going to summarize all of this stuff in the term like social intelligence here. There are other terms you could use. If you want mission success, you need leadership and you need teamwork, and you need everyone to have social intelligence. The technical excellence is important too, but it's honestly kind of secondary. I think technical excellence is easier to come by than social intelligence. It's an easier skill to gain, in my opinion. Okay. People sometimes call these soft skills. I think that's a poor term because they're really hard skills to learn and they're really important. They've got to be actively practiced. Okay, so this is kind of like my advice to you on practicing these. Uh, I mentioned earlier, like I had people recognizing the potential in me. So take time to recognize the potential in the people around you. Um, Extremely important. Help them develop it. Help them meet their goals. Help them feel accepted and have their backs. Yeah. So this is I think your end of the bargain for engaging with your community, whether it's the robotics department or whether it's your group of friends or whether it's some team you're part of outside of school. Like this is so paramount for you to succeed and for your community to succeed. Um, Robotics has these three values on the website. One of them is robotics with respect. I think you all have it on like t-shirts or something now. It's not just some phrase that's like nice to write on a website or nice to put on a t-shirt. It's actually kind of the key to succeeding in a mission, succeeding in an ambitious mission, doing something we've never done before. Um, okay, so that's what it takes to get the samples back from Mars. Um, that's my talk. It's time for the Q&A, and I'm really eager to talk to you all. So yeah, tell me what's on your mind.